Welcome to the Chem 126 video lecture series. In this series of lectures, we will be exploring chemistry, a science for all seasons. Chemistry is a field that influences every aspect of our lives. Everything that you see, touch, feel, and smell are made out of chemicals. From the food that we eat, to the air that we breathe, the clothes that we wear, and the buildings that shelter us, all composed of different chemicals. These chemicals are made out of smaller building blocks called atoms. Throughout this course, we will learn the fundamentals of chemistry down to the atomic level, and then apply them to a variety of different real-world examples, exploring topics like air, water, and nutrition. Chemistry is a science dedicated to understanding matter and its changes. Matter is what makes up everything, right? Atoms make up everything. Molecules make up everything. And so in chemistry, we're going to look at how different atoms can combine together to form larger molecules, and how these molecules form things like materials and different substances. So the structural element, you can almost think of like Legos, right? In a set of Legos, we can put the different Lego pieces together and they connect together in certain ways, and we can build some sort of larger structure out of that molecule. And that's where we get into chemical reactions and physical changes. Once we learn a little bit about how the individual atoms work, we can combine different atoms together in chemical reactions, and they can compose larger structures, and these structures can lead to physical changes. So in the first half of the course, we're going to be looking at how we can build larger molecules with different atoms, and then how they can interact with each other through chemical reactions and physical changes. Then in the second half of the course, we'll look at how some of these reactions and physical changes can be related to real-world examples and how they're useful in different settings. Everything around us is made out of atoms. Everything that we see, touch, eat, exist as are made out of atoms. From the desk that you're sitting at to the chair that you're sitting in, your water bottle, the water in your water bottle, and you yourself are all composed of atoms. So one of the questions, just to kind of get us started here, is it true chemistry is bad for us? This is an interesting question to think about. Often, sometimes in the media, we might see different chemicals that are bad for us. So there are some examples, right? If you were to consume a chemical which is toxic, that would be an example of chemistry being bad for us. For example, the different pesticides that are used or different poisons, right? Venom from snakes is some sort of chemical. These are going to be toxic. Cigarette smoking, you're inhaling hundreds of different chemicals. If you're smoking a cigarette, many of these chemicals can lead to cause cancer. So this would be examples of chemistry that is bad for us. What about chemistry that's good for us? When you eat, we absorb all the nutrients from the molecules in the food that we eat, and our body can convert these nutrients into our skin, our bones, our organs, different enzymes and proteins that are necessary for life. This is also an example of chemistry. If we're sick and we take some sort of medicine prescribed by a doctor to help us feel better, this would be an example of chemistry occurring that is good for us. So chemistry is not necessarily bad for us, it's not necessarily good for us, it just depends on the type of chemistry that's occurring. Every interaction that occurs within your body, between your body and the environment around us, is generally some sort of chemical interaction. Science is the process of seeking and understanding the underlying principles of nature, and we can pretty much break it down into two categories. The first one is just the thought process of how do things around us work, wanting to understand how the world works, why are things the way they are. So this is the theoretical or philosophical question. Why does the tree why does the apple fall when you release it from your hand, right? Why does the tree grow? Why do the leaves turn colors each season? So these are speculations about nature. This is the original philosophical view that was not testable and existed before scientific and experimental method were employed. Then we have the technological facet, which is where we can actually take the knowledge that we learn and apply it for use. The application of the knowledge can be used to develop different technologies, different instruments, different tools, and used to further the advance of civilization. Around 2,500 years ago, Greek philosophers attempted to formulate their theories into technologies and used rational explanations. And so some of the original technologies that were developed were things like fire, the formation of beer and wine through fermentation, and a lot of these were prepared through trial and error and not necessarily a rigorous scientific approach. Science grew out of the natural philosophy of this speculation of nature. And so some of the original science, the original chemistry, is rooted in the form of alchemy, which originated in around 700 BC and spread across Europe into the Middle Ages. A more modern approach to the scientific method and scientific knowledge was originated with Francis Bacon, who is a philosopher and lawyer and judge. And what the philosophy that he preached was that science would solve the world's problems and enrich human life. And he thought that science knowledge could only be based upon inductive reasoning and careful observations of the events in nature. And so this approach could be achieved by the use of skeptical and methodical approaches where scientists could avoid misleading themselves. What are some fields which have been improved by chemistry? Almost all technologies have been improved or developed by chemists. Chemists have worked to develop technologies like the chips in the computers, technologies like different materials. There are some chemists that specialize just in creating new polymers, new plastics. Most of the materials and technologies around us have been developed by chemistry. Chemistry also improves health. All of the medicines and therapies, different therapeutics, drugs, these are developed by chemists. There have been significant food and agricultural developments that have been assisted through chemistry. When we look at things like genetically modified organisms, things that can help increase the growth of crops, make crops grow at a faster rate, larger amounts. These are all different chemicals that have been developed to assist in the food and agricultural industry. Also different types of chemicals that are used to prolong the shelf life of different foods so it can be distributed to a larger amount of people. When we're thinking about green chemistry, we can think about also some of the energy requirements of modern civilization and the different types of renewable energy sources that have been improved with chemistry, specifically thinking about nuclear energy as a chemical reaction that occurs that has been developed by chemists. All of the materials and manufacturing that are used to create different types of things like clothing, structural pieces like different plastics and polymers, and then finally the production of different metals and alloys has been improved through the use of chemistry. So, now we talked about, is chemistry bad for us? And we've also talked about in the last slide a lot of examples where chemistry is really useful for us. but there are some examples where chemistry is bad for us. And in 1962, Rachel Carson, who's one of the people who's inspired the grassroots environmental movement in the United States, came out with a book called Silent Spring. And in Silent Spring, she repeatedly suggested that the use of chemical pesticides to control insects was also threatening and destructive to other types of life. And so this actually was the grassroots movement which led to the creation of the EPA, or the U.S. Environmental Protection Agency, and she was awarded a Presidential Medal of Freedom by Jimmy Carter for this. But from the 60s onward kind of came this thought process that we have to be responsible for the science and the chemistry from a biological standpoint. How is it impacting the environment? And this was the beginning of some of the regulations that we see on a lot of the chemical and biology industries. So next, let's go through some of the characteristics of science and discuss a little bit about the scientific method. So science has 5 major characteristics. First of all, it's testable. We can observe or detect a variable. You could come up with a hypothesis about if something occurs or not, and then look at some sort of variable that's testable. Science is also reproducible. In order for us to come up with some sort of conclusion, that conclusion has to be based off of something, some sort of experiment or evidence that can be reproduced. So we can get the same conclusion every time that we run the experiment. So reproducibility. We can't just run an experiment once and say, okay, then it must be true. In order to say that we think it's likely for it to be true, we have to be able to run the experiment over and over again and get the same reproducible result. Third, scientific characterization it must be explanatory, meaning it must make sense of observations. Fourth, it has to be predictive. We can take something that we've learned through a scientific hypothesis or experiment and apply it to a different situation. And then finally, and one of the most important parts, is that it's tentative. Science is flexible in that if there's a new piece of data, if there's a new variable, if there's a new component that we didn't know about originally, we can change our hypothesis or change our experiment to make sense of this new data. And so it's tentative, meaning that nothing is definite. We're not going to say, we know this is true without certainty. Instead, what we can say is, so far all of the data has shown that this is most likely the thing that's true. But we can't say this is true without a shadow of a doubt. And so in order for us to be able to illustrate these 5 characteristics, there's a process that we go through, and this process is called the scientific method. So it begins with some sort of observation of a phenomena, and this is what kind of instigates the process. Maybe multiple people will observe the phenomena, so the observation is then confirmed by others, and from this a hypothesis can be formed. And this is a question that's formed in a refutable statement. Often, the experiments are designed to test the hypothesis. Sometimes you can actually form a hypothesis based on some other experiments that you've seen or some other data that you've seen. But whatever our hypothesis is, we can then compose some sort of experiment that will help us figure out if our hypothesis is correct or incorrect. Really, we're looking to disprove our hypothesis, so experiments that can be used to disprove the hypothesis. Experiments are then designed to test the hypothesis, and there's 2 possibilities for the hypothesis at this point. The hypothesis is rejected. This is what we're attempting to do with these experiments. We're trying to refute the hypothesis. And if this is the case, then we go back to step 3, and we can form a new hypothesis based off of these observations, based off of this data. Or if data is consistent with the hypothesis, now it's important to note here, the data doesn't necessarily prove the hypothesis, it's just consistent with it. It doesn't disprove it. And then if this is the case, we go on to number 6, which is we come up with new experiments, or we repeat the same experiment to produce more data towards the hypothesis. Then, once this occurs many times, we can come up with theories or laws, and then later we can form additional hypotheses based off of these observations and experimentation. So the scientific hypotheses are testable explanations of observed data. And these hypotheses are tested by designing and performing experiments where we're only changing one variable at a time. So this is an important part here. Only one variable is changed and all the others are held constant. So in a lot of cases, we have to run many experiments where we explore each of the variables one at a time. This would be an example of a hypothesis and an experiment related to that hypothesis. The hypothesis could be that the HIV causes AIDS. And in order to test this, we could run the experiment where we inject a single infectious agent. So we inject HIV into an HIV-free subject and then follow it up with testing. And over time, we could kind of observe if AIDS forms or doesn't form in this subject. If AIDS forms, this would be data that's consistent with the hypothesis. If HIV doesn't form, this would be data that would reject the hypothesis. When we have enough data that is consistent with a hypothesis, we can create what's called a scientific law. And a scientific law is summarized with a large amount of data that provides a description of a natural phenomena, and a scientific law is always true and consistent given a specific circumstance. And most of the time, the scientific laws can be explained with some sort of mathematical equation. In contrast, a scientific theory is a set of tested hypotheses that explain a natural phenomena. The best way that I like to think about this is that it's our current explanation of something, but it's still able to change. Theories are always tentative. Just because it's a theory doesn't mean it's not necessarily true. So there's a few, popular scientific theories, like the Big Bang Theory, atomic theory, and the theory of evolution. These are all most likely true, but currently this is only our best guess of what's actually occurring. And so all of the data that we have, all of the observations and data that we have, all confirm these theories. It's all positive data towards them. We don't have any data that disproves these theories. So this brings up a follow-up question. Can a scientific theory be proven? Some people think that science is absolute, but that's not true. A theory is always going to be tentative, and based off of future observations and future data, a theory can always be modified. A theory is simply the best summary of our current understandings of a process. It's not going to be something that we say we are certain is true without a shadow of a doubt. It's a law that says this is why we think this happens, or this is why this happens. It's not a law that says this is how this happens.